Well, thanks for inviting me, and it's an exciting opportunity to interact with all of you. This is a talk that mostly the sort of meat of the talk is new work from my graduate student, Jeff Coburn, who's shown here. He was actually preparing a lot of these slides. He's been working on this, we're working on it together for a while, and a lot of the slides were prepared literally yesterday. We're going back and forth until the very last minute. So some of these slides are almost the first time that I've seen the slides, so we're sort of going to be looking at the data together. But hopefully I'll be able to motivate the problem properly. And the first part of the work that I'll sort of only briefly sketch out in terms of motivating the information-seeking part is what really is a long line of work by Anne Collins, who's a very talented postdoc in my lab. But I'll start out sort of more broadly motivating a question that I'm not at all an expert in, but I think it's kind of a fun question to motivate this problem. Which is something that's always bothered me, which is why is motor learning so slow in humans? So when people are born, they really can't do a lot. They can't move very well. If you compare them to, for example, these kittens that are a few weeks old, and they're doing these sort of marvelous feats of fighting with each other in ways that are pretty impressive. And then this is a picture of my two twins when they're a few months old, and they're kind of lying on their back, and I wanted to be proud of them, but they weren't doing much really at all. And the standard story for why that might be the case is that human infants are born early because their head is big and the size of the birth canal is small. And so what really is needed is a fourth trimester that after the people have been born, they have an extra trimester to do the kind of development they would normally do in utero, and then they should be sort of good to go. And while I'm not denying that there's some validity to that, I don't think it can be the whole story. So if you look at what happens after the fourth trimester, so you could look at what happens after 3 months and look at the milestones of human performance from babycenter.com, which we use a lot as parents, looking at what the milestones are. The milestones are, you no longer need to support his head. When he's on his stomach, he can lift his head and chest. He can open and close his hands. It's not really mind-blowing stuff compared to what we see in the kittens. Like the humans are still, this is basically my kids at that age. Now they're almost 3 years old and they're doing all sorts of impressive things, and I am proud of them, so I just have to say that. But my hypothesis for why this might be the case, and it's really a speculation that will relate to some of the work that we actually do in adults and a little bit developmentally, is that the human brain, or the primate brain, is wired to discover latent generalizable structure. So there's some structure in the world, and it takes some time to actually discover that structure. And so initial learning about what actions to take in the environment is actually going to be slower than a system that uses a very basic flat reinforcement learning system. But once you discover that structure, you're going to be much more flexible and generalize it to different kinds of situations. So Anne has done a bunch of work to try to establish that, not in babies, but just computationally and in adults, and I'll just start to motivate the problem in terms of this structure that we refer to as task set. So a task set is really just a linking between states of the world, actions that an agent can take, and the outcomes that they observe, and that there might be some context or some cue in the world that tells you, here's a task set that's valid now, and here might be, in a psychology experiment, a very simple one, you might see something like this, the states of the world are just these different shapes, and the actions that lead to the best rewards are these ones, let's say A1, A2, A3, and this entire thing is a structure of a task set, which might get cued by, in this case, a color that tells you if the color is orange, then this is how you respond to shapes. But you could just simplify the notation here and say S's lead to A's. And then it could be that you see some other context in the world, in this case another color, and possibly for the same low-level shapes, they might have different actions that are rewarding. And so you have to learn both the mappings between shapes and actions and outcomes, but also the mapping between which context in the world cues which of these structures. And there could be many such contexts. But the problem is that the task set, and task set space is actually latent. So it's not really that you want to link directly colors to state action mappings, because it could be that there are many such colors, and regardless of how perceptually similar they are to each other, that all cue the same basic task set. And so a priori, we don't know the size of this task set space for like the number of contexts, how many task sets there truly are. And we also don't know the mappings, and so you would have to learn both these mappings and these mappings. And so yeah, this is showing that the task set space is latent. And then one question might arise is what happens if you get to a new context that you've never been in before? What would you do? And you could say, well, maybe I'll just try the most popular task set across contexts, regardless of how often this task set has been used in any one of the contexts. The idea is that you would sort of group your prior for trying out one of the states would depend on the variability across task sets in which, across contexts in which that task set is applied. Or maybe you'll try the other one, which is less popular, or maybe in some cases you would need to create a new one altogether because the rules don't apply. And you can think of many situations in the real world in which this applies. For example, going to England, the driving rules are very different than they are in France and in the US, and you don't want to necessarily learn as if those are the same place. So we have models that essentially formalize this idea that you're clustering context around task sets. But because I actually have less time than I thought for this talk, I'm not going to go into the details of that. Essentially, it's the model is a formalization of this clustering process, which is based on the Chinese restaurant process, if you're familiar with it, which is an elaboration of some of the work that Sam Gershman, who's actually talking next, has done in Pavlovian conditioning. And we've also shown that you can implement this kind of thing in a hierarchical model of the prefrontal cortex and the basal ganglia, where there's like a loop that selects task set representations that are really abstract in prefrontal cortex in response to contextual stimuli, and it learns through reward which task set representations should apply, and then those don't actually mean anything in advance, they just act to contextualize the selection of lower level motor actions given states of the world. And it turns out that there's actually a pretty nice mapping between this hierarchical model of neural circuitry and the high-level process that involves sort of clustering context in a sort of Bayesian kind of way. And I'm going through this quickly because I really want to motivate the information seeking problem, so I'm just going to skip on to the next slide. This is just a summary that N has done a bunch of work showing that people seem to be building these hierarchical structures of context that queue task sets that then queue which actions to select. And she's done a bunch of empirical work that suggests that people do that sort of spontaneously and that you can see it in their EEG signals. But a motivating question is, how can we actually actively select actions in the world that will inform us about this latent state? But what is the relevant task set? What is the task set that applies that dictates my behavior? And the work that we've done in that domain so far really has been about inferring what the task set is, but not about how you can optimize your policy of what actions should you choose that would give you information about the task set, especially even if the actions themselves are not and even have no potential to give you reward. So that there might be something that's diagnostic, actions that you can take that's diagnostic about these latent states, but don't necessarily give you reward in and of themselves. So to get at that, this is now the work of Jeff Coburn in my lab. He uses a task where humans are faced with choosing amongst different cards. And I'll just try to break this down. For this particular card, let's say it has a sun on it, there's two possible outcomes. You could win $50 or you could win $0. Same thing for this card, also has two possible outcomes, 50 and 0, but you'll see how they differ in a second. There's a third card that has an outcome that's only always $5, it's a sure thing. And then there's another card that gives you either $4 or $5. So far it seems like why would you use this design, but the actuality of the design is that there's two effective task sets where the contingencies are defined by different decks. The subjects know this. They say that they're either in one deck or in the other deck. And it turns out that the first deck is defined such that the probability of observing outcome 1, which is a high reward, is, let's say, 40%. So the expected value of that card is $20. And for the second card, the probability of observing that big win is only 10%, so its expected value is $5. So if you knew this, you should always choose that over that. And in the task that people are going to do, we actually tell them of the contingencies, but they also get to experience them and see what they feel like. Well, just hold on a minute. And then before we look at the other decks, look at other cards, look at the other deck. These two cards in the second deck are just reversed in this particular case. It doesn't have to be a straight reversal, it's just a contingency change. But in this particular case, now this guy has a 10% chance of a high reward, this one has a 40% chance. So if you knew that you were in this deck, you should reverse your policy and choose this one instead of that one. Is that clear? Yeah. Okay. So the other cards, why do we have the other cards? Well, the final card is really the most interesting one. So this one has an outcome of either $1 or $2. But in this deck, the probability of observing $1 is 100%. And in this deck, the probability of observing $2 is 100%. So the probability of observing 1 is 0. So what that means is that the expected value of this card is $1 here and $2 there. In both cases, it's actually the worst card in terms of rewards, and I'll show that in a minute. But it actually will give you some information about what deck you're in. So let me just highlight that first. If you look at it in terms of rewards, the green is in this deck, green shows the most rewarding option. And in this deck, the green is the most rewarding option. And you can see that the red one has the lowest expected value. We also have this third card, which gives you a sure thing every time. And that's essentially going to be a control because we want to make sure that any selection of the informative card, so this is actually going to give you information about the deck, that it's not because you're more likely, you want to have sort of consistency in your predictions. And so we want to control for that to just make sure that people are not always going for the sure thing. And this thing, in this case, it's perfectly a sure thing across both decks. Okay, so in terms of information, you can quantify the mutual information between the outcome that they observe.
I don't understand why on the right-hand side one, for example, in the top, you say that the outcomes can be $1 or $2, when actually it can only be $1. So the outcome of $2 is never realized. In that
no, it is. Sorry, maybe it's not clear. So the probability of $1 is 1 here,
yeah,
and it's 0 here.
But for example, in deck 1, there is no probability of $2.
Oh, that's right. This is meant to be if you average across the decks. These are the possible outcomes. But the subjects initially are given training when you say, now you're in deck 1, here are the contingencies, now you're in deck 2. I'll show that next. But later on, we remove the information. So they have to sort of infer.
They learn by experience, right?
They have to infer what deck they're in. And so without that information, you could say, well, for this card, you can get either $1 or $2. But if you knew what the deck was, then it's only $1 here, it's only $2 here. Okay, so if you quantify the information available in these cards, it's clear that the last card has the most amount of information because it tells you deterministically that its outcome tells you what deck you're in. But I already just told you that it's also the least rewarding card, so that there's no reason to choose it based on just its reward. But it's not the case that it's the only one that has information, right? So you can quantify, this is the mutual information between the outcome and the deck, so how much you reduce your uncertainty about what the deck is when you know the outcome. And you can see that in this particular case, there's some mutual information in the actual rewarding cards because every time you observe an outcome, it gives you some information about whether it's more likely to be one deck or the other. And depending on what these contingencies are, these rewarding cards can also have more or less information. But we always make it so that the final card has the most amounts of information. And so if you just highlight where the information is, it's this card has the most information, and this has the consistent one has least information, and these guys have some amount of information. Okay. So the task dynamics are such that initially we give them training and we just tell them, now you're in deck 1, you get 10 trials, now you're in deck 2, and you switch back and forth so they get to feel like, experience what it feels like. And then we just say, okay, go, play, you don't know what deck you're in, but try to guess what deck you're in and try to maximize your rewards. But we tell them explicitly that there's a hazard rate and that there's a probability that the deck will switch on every trial of 5%. So it's not going to be a reliable, like 10 trials switching, but rather there's just a 5% chance that the deck will switch. And so it could be something like this, T equal to 18 for deck 1, and then 26, and so forth. Okay. Okay, so first what we can do is define what is the optimal model to actually perform this task. And to do that, we use something that's like the Giddens index, if you're familiar with that from reinforcement learning in the sort of explore-exploit trade-off, although it's not formally identical. But essentially, all you're doing in this case is saying, what is the reward that you can compute? What is the expected value of any of the cards, given your current belief about what deck is in play? Given that you're going to select just one trial, and that's easy, right? The expected value of choosing a card, if you knew that you were in deck 1, the first one would have $20 or whatever it was, But the problem is that you have to sort of roll it out into the future, because you could say, well, the value of choosing the informative action has a very small reward value, but if you knew what its value was, if you knew what its outcome was, then your prediction about what deck was in play on the next trial would be better, and your ability to harvest reward on the next trial would go up. And so you can roll that back into the reward value of choosing the informative action at the top level. But it's actually a really complicated thing, because you have to think not only how it's going to influence your behavior on the next trial, but trial after that, and the trial after that, and so forth. And then you also have to take into account the hazard rate, that there's always a fixed probability that the decks will switch. So there is a way of simulating and computing what the optimal policy will be, and we'll use that as a benchmark. But we don't actually think people are doing that, because it requires a lot of computation. Just to show you what the effect, though, is in this optimal model, if you use a one-step horizon where you're only considering your current trial, you can say, what would the model do? And so if it has a belief that the deck 1 is in play that's greater than 50%, you can look at what is its chance of choosing the high rewarding card from deck 1 or the high rewarding card from deck 2. And it's just a simple policy where here it always will select the more rewarding cards, the card 1 or card 2, and it will not select the informative card. But as soon as you allow for it to consider horizons, a few trials in the future, then it starts to select the informative card, even optimally based on its value, particularly when you're uncertain about what deck is in play. So when the probability is at 0.5, you have the highest amount of uncertainty. And that's because if you select it in this trial, it'll allow you to harvest rewards by maximizing in the next few trials. And then that goes up if you allow for a 6-step horizon, then the value of the informative card goes up even more. Turns out that 6 cards is the asymptote here because of the hazard rate, that you can't do better by looking forward more than 6 steps. Is that clear?
So is this assuming that the subject is completely tuned to the probabilities already?
Yeah, so they're
So
told
these optimal are not including the exploration phase.
it's optimal assuming that you know what the probabilities of each deck are and you know what the probability of switching is.
The one thing I didn't get is that if they only have 10 trials, how could they infer all the probabilities?
They're told the probabilities.
And what?
They're actually told the probabilities explicitly. The trials are just to give them a sense of what it feels like to be in this task, because explicit
And you
instruction of
have an
probabilities.
independent control that they know what the probabilities are really. So when you tell them.
We tell them, and then we remind them before the test phase, and then they're reminded every 50 trials. So they should be, in essence, we don't even have to train them, but we feel like it's better to train them, because you want to know, when you say something is 60%, well, what does that actually feel like when you're going through sampling? So that's why we give them the training. And it's not only 10 trials, it's 10 trials, and then another 10 trials, and then back to 10 trials, so they get that over and over again.
Sorry, just kind of question. So what here when you say 6-step, is they sample 6 cards from a deck before making a decision?
No, so 6-step means that if you're going to consider what is the expected value of choosing the rewarding cards versus the informative card, if you're going to consider what is the value of, if I knew the outcome of what deck I'm in now, how well could I do for the next 6 trials after that, or 5 trials after that, right? So if you're allowing yourself to consider the influence of knowing something in the next few trials, then the value of choosing the informative card now goes up, because you could then exploit it on the next trial. But as I said, I don't think that people are doing the full optimal solution, but we have a heuristic model that tries to approximate that. So the heuristic model keeps track of the probability that each deck is in play based on the outcomes that are observed. And I'll show you how it does that in a minute with an ideal observer. But then what it does is it tries to predict when people are going to probe. And when I say probe, I mean choose the informative card to get some information about what deck they're in. And the idea is that you should probe when you're most uncertain about the latent state. So that sort of intuitively should match when you would want to get information, you're uncertain about it. But also when the action is most informative about what the latent state is. So you have to compare the information about the most informative card relative to how informative the rewarding cards are in and of themselves. So a simple equation here is to say that the subjective value of choosing any given action is going to be equal to its expected value assuming no information, just knowing its reward value in that trial, plus two factors. One is the uncertainty, so stands for entropy, so it's just the entropy in the belief about what the state is. So if you have a belief that the state, you think there's a 50% chance you're in deck 1 versus deck 2, then you have maximal uncertainty about that, and so that would be high. Multiplied by the mutual information between the outcome of that action and the latent state, meaning how informative is that action about the latent state. So for the informative card, this is the one that's always going to be high, and for the rewarding cards, depending on the contingencies, they'll have some amount of information. So this is the first heuristic model. There's variants of it where you might notice that basically what you're doing, you're saying you value something based on how rewarding it is and how informative it is if you don't know what the state is. But you might notice that this doesn't take into account how valuable is it to even know what the latent state is. So there might be situations in which it doesn't really matter so much if you know the latent state because you're not going to change your policy that much from one deck to the other. And so you can modify this to incorporate some value in there, but we can talk about that later. For everything that I'm going to talk about, we're just assuming that effectively you're adding value to information. And another way of writing that is just this, expected value plus sigma as a measure of how uncertain you are times the information. It's just shorthand. Okay, so how do you infer what the latent state is itself? Yeah.
So just a question about your previous equations. You don't take into account the temporal expectation of your task. I mean, if you just have the one trial or several trials, this is not included in your.
Well, actually, so it is
or?
here, right? So we have to be able to predict what the latent state is, and so what we assume is that people are keeping track of that latent state in this way. So before they make a choice, they have some probability that they think they're in deck 1, and their new probability before they even make a choice is just that same thing plus keeping track of the fact that the deck might switch, and you know that there's a hazard rate of 5%. So they have to allow on every trial that whatever their previous estimate was, it could change. But then after they observe the outcome, they can now do the posterior update just based on simple Bayesian updating to say, what is the probability that I'm in deck 1, given that I've observed this new observation? Okay? And so it's just an ideal observer on that. Okay, so let's get to some empirical data, and I'll get back to some modeling later. We can see what people choose overall. They choose the large reward the most, and then the small reward, which is still more rewarding than either of the other actions, the next most. They choose the consistent card that gives them a sure thing every time, that has a larger reward than the informative card. But they still choose the informative card some of the time. This is just overall, so we'll get more informative measures in the next few slides, but this is just showing overall people do choose the informative card. And they choose it less than the consistent card, but the fact that they choose it at all might suggest something, because the consistent card always has a sure thing and it always has a higher reward value. And so what are they doing with this informative card? Are they doing what we think they're doing with it? So one thing to do is you can compare the condition that I just told you about, which is here, to a condition in which what I'm calling the informative card, instead of being informative, its outcomes are just random. So instead of being $1 in the first deck and $2 in the second deck, now it's like Alex was asking, it actually could be $1 or $2 regardless, and so it gives you no information. And so people still choose it in that case, but they actually do so significantly less. Maybe hard to see that here. It's within subject design, so they definitely choose the informative card more when it's actually informative than when it isn't informative. And in fact, I think that some of the degree to which they choose it here is because they think it could be informative, but it actually isn't. And I can get into that later. But this is the first sort of control to suggest that this is significantly higher than that. But another thing you can...
They also do more recording when they don't have the informative card.
Yes.
Right?
Right, oh right, I forgot to mention that.
Right.
Yeah, so that's actually really critical. So they're actually using the information here to be able to differentiate between the high reward and the low reward. And here, they sometimes use the informative card but it's not informative, and so they actually don't actually discriminate between them. The contingencies in this case are actually really difficult. 40-10 reversals are pretty hard. And it turns out that even though it looks like they're choosing the small card more than the large card, that's because of, if you look at what their actual optimal belief should be about the deck, that's not quite the case, and I'll show that in a minute. I'm gonna just skip this. Yeah, I'll show this. Okay, what this is showing is, actually no, I will show this first, sorry. This is showing as an inference about what the probability of which deck is on the x-axis, the probability of choosing the high reward card for deck 1 and for deck 2. And so you get the x function as you would expect. They're really differentiating between the two rewarding cards in the informative condition, and they're doing so less in the uninformative condition. But they still are in the right direction. So the reason why it looked like in the wrong direction before is just because after a reversal in a 40-10, the optimal model actually thinks that the previous state applied for a while. So if you actually condition it on what their inferred state belief should be, they're doing the right thing on average, they're just not doing it as well as one in the informative part. Don't worry about these ones because they're actually not informative the way that's plotted, but if I plot it this way, now on the x-axis is what the, instead of the probability that a deck is in play, it's the uncertainty or the entropy. And this is one of the first critical pieces to show that the probability of choosing the informative card goes up as they should be more uncertain about which deck is in play. And as a result, their probability of choosing the other cards goes down. And that effect of uncertainty is not there in the uninformative condition. So that suggests that they're actually using uncertainty to guide their selection of the informative action when they can get information, but not when they can't get information.
Never mind, actually makes sense.
Okay, so that's starting to be.
Just remember, the consistent card is always the worst card, right? There's really no reason to.
Well, there's no reason to choose it, but people like consistency.
Even if it's just to run everything the other three is better than.
What's that?
You should not never get the consistent card, right? Because it really works.
You really shouldn't, but sometimes people like a short thing, and these are actually weights from a logistic regression of the influence of these factors on probability of choice. So there is a weird pattern here where it looks like they're choosing the consistent card the most when they're least uncertain, and that's really weird. But it's actually that there's very few observations at this point where people are really uncertain, and so if we had variance on the on these weights, these would actually be really uncertain. And there's just a couple of cases where people happen to do that, and so I don't think that this thing actually is meaningful, but we'll see with more subjects, because that's a really weird pattern. You would expect of anything the opposite, that they should choose consistent cards more. If they're most uncertain, they might as well say, well, I'll go for a short thing when I don't know what's going on.
Have you tried to change the ratios between values, because this is very dependent on have you tried to change the ratios, because the optimality depends on the 20 being 4 times bigger?
Yeah, so that's what I'm getting to next. The question was whether we've changed the ratio and what the actual values are of the rewarding cards relative to the informative cards and so forth. So all this is so far for the contingencies that I told you about with 40, 10, and the expected values that I told you about. But at least what we've shown within these contingencies is that there is an effect of uncertainty in the degree to which they're choosing the informative action, and it's only there when it can be informative. Okay, so this is actually getting at the question you're asking is what are the costs of information? So there's a benefit to information, but there's going to be a cost of information because every time you choose the informative card, you're foregoing the opportunity to get one of the rewarding cards. And remember that the second most rewarding card in each deck is always more rewarding than the informative card. So even if you don't know what deck you're in, sometimes it might be better to just choose one of the rewarding cards regardless of which one, because the second most rewarding card still gives you some amount of reward. But it's not as much rewarded as you can get, so depending on the horizon and depending on these things, it might change. And so here's a case where there's low cost of information, so it's a 40-10 contingency. The expected value here is 20 versus 5, and 20 versus 5. But in the high cost condition, the values of choosing the rewarding cards are really high. So the expected value is 45 for this, and still $30 for the second most rewarding card, and just the opposite the other way. So in this case, the reward values are higher for the rewarding cards, which means the cost of choosing the informative card goes up because you're foregoing the opportunity to get that. And this is basically balanced, these low, medium, and high cost conditions are balanced for how informative their rewarding cards are themselves, if you look at the usual information. So you can look at what happens according to the optimal model, and there what you can see is that when there's low cost is when you see that the optimal model chooses the informative card when it's most uncertain a lot, but then that goes down, so when there's high cost, it actually will say, I'm never going to choose the informative card because it's never worth it to me. It's always better to just choose the second most rewarding card or the most rewarding card, and you're not going to do any better by knowing the informative state.
Sorry, and this is even with the horizon.
Yeah.
Even with the horizon, because of the hazard rate that we choose, so you only get a horizon of 6, and so you don't go beyond that. So,
And
yeah, I mean,
even so,
you could
you
choose
don't-
values where it would still be, but in this case, with this amount of cost, it's never worth it, according to the optimal model. But according to the heuristic model, it shows largely the same patterns, that it is actually sensitive to cost, even though, and that's because it's essentially you're looking at the effective value plus the effective information, and so value is going to have an effect. Although it predicts more probing for low cost condition, and also predicts that probing goes down with cost, but that you still get a little bit of probing, because it's not as sensitive to the true optimal values as the optimal model. And so the actual data show that if you look at the degree of choosing the informative action according to low cost, medium cost, and high cost in those conditions, it does go down, and it doesn't go down to 0. So consistent with the idea that people are sensitive to cost in a way that both the optimal model and the heuristic model will predict, but it's somewhat more consistent with the heuristic model in the sense that they're still probing even when there's high cost and they shouldn't be. But in all of these cases, low, medium, and high cost, the effect of probing goes up as a function of uncertainty. And especially in the high cost condition, the degree to which they probe is really strong only when they're really uncertain. Okay, so you can look also at a trial-by-trial response pattern of the individual subjects. And so what this is showing is the black ticks are showing when they're choosing the informative action, when they're probing. And in red is the ideal observer about the state belief, about what deck is in play. Or actually it's the uncertainty about that. And so one thing you can see is that initially they seem to do a little bit of probing almost regardless of how uncertain they are. But they get into this phase where then they start to probe every time this uncertainty value reaches some threshold. And it's not that they're just doing a rule of like 3 in a row of negative outcomes, I'm going to probe, but rather they seem to be accumulating that uncertainty up to some threshold and then probing. What the blue line in here is what the optimal value should be if the horizon was 6, according to the optimal model. So for this particular subject, it actually looks like they settle into a state where they probe when they reach a threshold that looks like what the optimal model will do. But there's a lot of variance across subjects. So some subjects will probe at lower levels of uncertainty or higher levels of uncertainty, and that's an interesting inter-subject, individual difference measure that we'd like to look at the basis for.
Sorry, forgive me,
Yeah.
it's my slowest. How do you measure the state of uncertainty trial by trial?
So this is just from the ideal observer. We know what it should be,
Okay,
And we just-
given its experience.
given his experience. Yeah. And so that's one of the limitations, that we don't know whether that is a really good model of how people are actually tracking the state of uncertainty. But if anything, people are, if you ask them how certain they are, they're more certain than they should be. And so we don't think that some of the variance of what we see and whether if they probe too much is really due to a bad model of their inference about the deck, but rather it's more about their policy given their inference. But there's more to be done on that. So this is really just saying how uncertain they should be given the statistics of the evidence.
But we don't see in this graph the effect of the outcome of the last trial, do we? Whether, for example, they are following something like we stay, we shift, something equivalent to that. If I've been lucky in the last trial, then I stay there.
You can't see that directly here, no, but because it depends on what your belief about which deck is in play, but your uncertainty should go down if you get rewards,
If you get it right.
for example. So you could look at places where like this might be when they got a reward, the uncertainty went down. Okay, so the last part I want to talk about is what about the non-pecuniary value of information. So pecuniary just means monetary value. So to what degree do people choose information even when it can't benefit them at all in terms of their value? So one way of doing that is to just say, what I've been talking about before is that there's two policies that you should have across the decks. In this one, you should choose this card, and this one, you should choose that card. But you can also set it up so that the policy shouldn't actually change. So you have 60-30 here, and then 40-20 there. The contingencies change, but the best card is the same. And so in this situation, knowing what the deck is actually shouldn't change what you do. And remember, they're told these probabilities, so really the best thing to do is just always choose this card. But if you really want to know what deck is in play, you still might probe in that situation. And you can look at it in the optimal model. In that case, actually never probes at all, which makes sense. But the heuristic model does actually probe because it's sensitive to information. At least the first version of the heuristic model that I showed you, it's sensitive to the amount of information that's there and the uncertainty, and it's not as sensitive to the fact that the policy doesn't change. And if you look at what actually happens, two policies, one policy, you can see that people are still probing in the one policy case. This is preliminary. It's actually few subjects, and right here I'm just averaging across all subjects, and not everybody shows this, but on average they still probe in the one policy condition. That's just the main thing to see here. This is the large reward and the small reward. But there's just one last point I wanted to make here, which is that the heuristic model actually makes a prediction here, which is that people should probe more when they believe that the low reward deck is in play. So this is showing the prediction of how much they probe as a function of how of their belief in which deck is in play. And you can see this is not centered at 0.5. It's actually shifted to the left, which means they would probe more when they think that the low value deck is in play. And that's essentially because the heuristic model says that you're adding value to uncertainty and information. And so if you believe that the second deck is in play, the second deck actually has a lower overall expected value. And so the effective information should go up relative to the effective value. And what this is showing is how, when people are probing, what their belief was, what their inferred belief was that the rewarding deck was in play. And when there's two policies, it's 50% as you would expect. But when there's one policy, they're more likely to probe when they think that the less rewarding deck is in play, which is the prediction of this heuristic model. All right, just very finally, we did some EEG with this and looked at, this is a site over frontal cortex that's sensitive to rewards early during the trial. So there are these potentials that are sensitive to large versus small rewards. And there are other correlates that are separately representing informativeness, separately from reward. So later on in the trial, over posterior sites, which might be something like parietal, but we don't really know for sure from EEG, you can see that when people are in a high uncertainty case, they really reliably differentiate between the informative of the card that they're considering now. So they have a differentiation of high information, medium, and low information. And that difference is only there when they're uncertain and not when they're not uncertain, when they're certain. So yeah, that's just some initial preliminary data that Jeff did on this. Conclusions, it seems like humans are building structure when they're doing reinforcement learning. They suggest that there are these hierarchical interactions between prefrontal cortex and basal ganglia, which I didn't have time to really go into, but that support the structured task set learning and also support transfers. One of the things that Anne has shown is that you can go to new contexts and transfer task sets that you've learned before to new contexts altogether. And maybe there's a role for that process in development. That's sort of the thing that I motivated at the beginning, but that's just for talk later maybe. But the meat of the talk focused on how people probe actions that are most informative about the latent state, especially when they're uncertain, and that can be captured by a heuristic model that combines these factors. And that EEG signals seem to represent value and information at distinct time points during the trial and in distinct electrodes. All right, so thank you very much.
We have time for questions.
So, in your heuristic model, these two terms are just weighted by one. I mean, but one is really, the first term is really kind of the monetary value, the second is information value. I mean, it feels almost to me there's a key parameter
there is a free parameter when you actually fit it to people, so or you can also generate relations that would differentiate between how much you weight information.
Yeah, so, but it could then also be that in your case where you play the game so that your decisions have no monetary value, that this factor is different. Or in other words, did you do really people who play this the game with the rules so that their decisions have no monetary value? Do they actually use the informative action at all, or do they just not use it?
Well, in the single policy version of it,
Yeah,
like when their policy shouldn't change,
yeah,
yeah, that's when some people do use the informative action.
which they do.
And they should. It's interesting though, because the people that do that, it seems like they're using a softmax-like choice rule, so the greater differentiation between the rewards, the more reliably they choose the higher rewarding option. And then when they switch to the other deck, even though the rewarding action is the same rewarding action, they differentiate between them to a lower degree. So it's as if they're probing in order to use the softmax choice rule that applies for each deck, which is not really the right thing to do because they don't have to explore and they know what the contingencies are. Whereas the people who don't use the informative action just always choose the rewarding card if they're not doing that. But it's preliminary, there's actually only a few subjects in that experiment, so we have to see whether that holds up.
It's a really lovely paradigm. I'm wondering how much your model would change, people's behavior would change if you had to simultaneously explore the world. Right now that they know everything about two possible worlds and they're using the informative deck to decide which world they're in.
Yeah.
And if they had to jointly infer the distribution of the probabilities and token which particular possibility they are in, can you model or how do you think this would affect either the model or the behavior? So if they didn't know the probabilities of the decks, nor did they know that there were two worlds,
Right.
and their exploration had to uncover all of this.
Yeah, no, I think the model would actually work the same, it would just have to learn the probabilities, and that's what I wanted Jeff to do initially, because I want people to just go wild, do reinforcement learning, don't use explicit judgments about things. But the problem is to test the different predictions of the models, you really need to have different contingencies and rewards in different decks. And in order to do that pragmatically, if you just have them learn it by trial and error, everything, it would just take forever. And so it was easier to run multiple conditions by giving them some information about what the actual contingencies are and running less trials of learning what those things are. But I think theoretically, we could do it between subjects, and theoretically it should work, but you're going to have more uncertainty at all levels, not just what deck is it, but what the contingencies are in each of the decks. But I don't think it actually changed the model at all. Good. Yeah. Sorry, I guess I went a little bit.
Okay. Thank you for your presentation. I have a question regarding the EEG analysis at the end.
Yeah.
So, what you showed. Yeah. So the EEG analysis that you showed at the end, these are the event-related potential. And so exactly when are you collected them when the user was looking at the card, or before selecting the card, or when he got the reward? At which point was it exactly?
They're looking at the card, and actually in the EEG version of the experiment, I skipped over this, but they don't actually see all 4 cards at once. They only see 1 card, and they have to decide, do I want to play this, or do I want to not play it and go for a gamble of like a 50-50 probability. And that's just because we want the EEG signal to be affected only by the value of that 1 card and that 1 stimulus. But yeah, it's when they're looking at that card, and you can look at how informative the card is and what its value is. And it's like a few hundred milliseconds after they see the card, they have some value and then some information.
And so in this case, could that be that the signal that you observed is related to the error potential? Because I guess maybe the ERP would be different according to how much they were expecting, because the difference between the expected value and what they actually get. So I don't know if it's related to this kind of signal or...
I think the reward value one might be related to those error signals, because error signals are computed relative to your average expected value. But that would still be consistent with representing value in some form. The later one that's on information and is modulated by uncertainty, I don't think could be related to errors.
Okay, thank you.
This is a very advanced version, very attractive version of a multi-arm bandit problem. When you do bandit problems, like very simple 2-arm bandit in animals, the greatest difficulty is to let them, I'm going to use the word, let them understand that, let's say, let's tune to the structure of the task itself. And here you are telling people what the task is, you're telling them the probabilities.
Yeah.
This makes it, if you were to do this in animals, for example,
Yeah.
you would have to teach them the time horizon by experience with the duration of context and things like that. There would be uncertainty at a much greater number of levels.
Well, but if you were to do it with monkeys, for example, you would have many more trials.
What's that?
You'd have many more trials, so
Yes.
they could learn those probabilities pretty
Well,
well.
can they? I mean, because part of the problem is that you have transient effects. So they don't necessarily understand that the probabilities in each deck are stable. You tell them, this deck has certain probabilities and that deck has other probabilities. If you do it in an animal and it has a run of good luck in one deck, it thinks that that deck is getting better now. And it has good reasons to believe that.
No, I think you can train monkeys if you need, for example, monkeys, I don't know about. But if you keep them in two contests that are stable over the experiment duration. So day after day after day, you can teach them red means 80% reward and green means 40% reward, and they will learn that. I mean, it has to be very consistent. But then I think switching between red and green will be easier on trying.
So they don't have to average across them, they would learn.
No, they will learn to
just
separate with a lot of experience, but yeah,
Right.
it's learnable. Yeah.
We did similar things with birds many years ago, so two unbounded experiments on birds. The problem we have in teaching our time horizon is that when the time horizon is long, the amount of reinforcement you get is greater because it's long, and it takes you sometimes longer to overcome. And the short time horizon, you learn less in a sense, or you haven't reached your asymptote. So however long you give them, you will have the problem of learning, separating strategic response to
Unless you allow them to revisit prior states.